In this video, we take a look at the 68, 95, 99.7 rule. This is also known as the empirical rule. This rule tells us in a normal curve the relationship between the mean and the standard deviations and then the total percents within each part of the curve. So we know approximately 68% of the observations fall within one standard deviation, noted with a sigma for a population standard deviation, away from the mean, noted with the Greek letter mu for the population mean. So we call this observation range typical, where the middle 68% of data lie. You'll be able to calculate this range by starting with the given mean and then adding or subtracting one standard deviation. These areas are calculated using a computer, so we'll see at the end of the video how we can verify our calculations in StatCrunch as well. So you don't need to use any formulas to find the area. You can either use the 68, 95, 99.7 rule, or you can use StatCrunch. We know that approximately 95% of the observations fall within two standard deviations of the mean, and this is true for any normal distribution, no matter how it's stretched or compressed. We call the observations that fall outside the 95% range unusual observations. And then approximately 99.7% of the observations, so most of the data, fall within three standard deviations of the mean. And we would call any observations that fall outside this range extremely unusual. I find it helpful to break up any normal distribution chart into the parts with the percents labeled so that I have an understanding of how much area is in each part of the graph. So I usually break up lines from the mean up to the first, second, third standard deviations added on and fill in the corresponding percents that match the values we see here in this chart. At the tails, the 0.15% go as far as the graph goes, so sometimes we put an arrow there to show that the graph could extend because we might not have found our minimum or maximum data point. You can also verify if you add up all the percents, they'll add up to 100% because this is a probability distribution. So we are going to look at vocabulary test scores for 7th grade students in Gary, Indiana. We're told that the distribution is close to bell shape, so we are going to call it approximately normal. We are going to use the fact that researchers have found that the distribution have mean 6.84 test score and standard deviation 1.55 test score. So we are going to use these values to fill in the normal distribution curve. So I start with 6.84 at the center of the normal distribution curve, and then I add that value 1.55 to fill in the higher marks for adding the standard deviations. So 6.84 plus 1.55 is how I got the 1.39, and these are vocabulary test scores. If we add another 1.55, adding two standard deviations, that vocabulary test score would be 9.94. So that would be a 7th grade student who has a 9th to 10th grade vocabulary score, and so that would be more unusual. That's why we're further out on the curve. When we add three standard deviations to the mean, we get a vocabulary score of 11.49. So that would be a very unusual 7th grader to have an 11th grade vocabulary score. Then to fill out the lower side of our distribution, we come back to the mean, which has the 6.84 vocabulary score, so just about 7th grade, which is where we expect a 7th grader to be. So we're not surprised that this is the center of our distribution. And then we would subtract 1.55 to get vocabulary score 5.29 at one standard deviation below the mean. If we subtract another standard deviation, we get 3.74. So now we're in unusual territory. We would be pretty surprised for a 7th grade student to have a 3rd to 4th grade vocabulary score. And then we subtract another standard deviation, so 3.74 minus 1.55 to get the 2.19 at the lower end, and that would be very unusual territory. It would be extremely unlikely or unusual to find a 7th grade student with a 2nd grade vocabulary score on this exam. So my next question is, what is the range of scores for the middle 68% of the data? And this is the range of values that are considered typical values for the distribution. So we can look back at our labeled distribution here. And so we see the middle 68% is one standard deviation below the mean, a score of 5.29, all the way up to one standard deviation above the mean, a score of 8.39. So I said here scores of 5.29 to 8.39 are the middle 68% of data. If you prefer just to do this by hand, it's not necessary to draw out the normal distribution curve. You can do the calculations because you know 68% correspond with going down one standard deviation and up one standard deviation. So you can calculate 6.84 minus 1.55 to get that lower limit of 5.29, and then you can add 6.84 plus 1.55 to get that upper limit of 8.39. Question C asks us to find the range of scores for the middle 95% of data. And so these are the values that we say they're not unusual. We're not in the highest or lowest 2.5%. So we come look at our distribution here, and following our labeling, if we go down 2 standard deviations, that's a vocabulary score of 3.74. And if we go up 2 standard deviations from the mean, that's a vocabulary score of 9.94. So quite a range. Vocabulary scores from 3rd grade all the way up to 9th or 10th grade. So we say here to answer question C, scores between 3.74 and 9.94 are the middle 95% of data. If you want to do it by hand without using the distribution, you can calculate as we show here. First of all, multiply 2 by the standard deviation. So 2 times 1.55 is 3.1. And then our next step would be to subtract that and add that to the 6.84. And we get the lower limits and upper limits that match our calculations here. Question D asks, what score is a cutoff where 2.5% of students score higher? So we come up to our distribution and we're looking on the upper side. So we want to look to see where's the upper 2.5%. I know the upper tail is 0.15%. So if I just keep adding, I'm going to add my percent areas here until I get to the 2.5% higher point. So 0.15 plus 2.35% is 2.5%, and that corresponds with a vocabulary score of 9.94. We say here that for scores of 9.94 and higher, the area above is 2.5%, since 2.35% plus 0.15% equals that 2.5%. Question E asks us what percent of scores are higher than 5.29 and what percent of scores are lower than 5.29. So to find scores higher than 5.29, we can add up the areas above 5.29. And I'm a little lazy, so I'm going to add that first 34%, but then I'm going to make use of the fact that I know scores 6.84 and above are the upper half of this distribution. So the area from 6.84 to the right is 50% of the graph. So I'm just going to add 34% plus 50%. And that is 84%. To find scores lower than 5.29, again, I'm going to be a little lazy and I'm going to say, well, I know the whole area is 100%, so I can just say 100% subtract 84%, and that gives 16%. Alternately, I could come up to my distribution and start over on the left side of the graph and add up the areas up to 5.29. And so that would be 0.15% plus 2.35% plus 13.5%. And that total is also going to be 16%. So either way, you can find the area here, whether you subtract 100% from the rest of the area or if you add up those groups of areas. Question F is a similar question. It asks what percent of scores are higher than 8.39 and what percent of scores are lower than 8.39. So this question here asks us to look at the value 8.39 that's 1 standard deviation above the mean. So if we come to 8.39 here and we add up the areas that are above, we see we will add 13.5% plus 2.35% plus 0.15%, and those values total 16%. I'm not surprised to see that because there's some symmetry. If we look back at the distribution, we know the area below 5.29 on the left side of the graph is 16%, and that's 1 standard deviation below the mean. So by symmetry, we expect the area higher than 8.39, 1 standard deviation above the mean to be the same area, 16%. And similarly, when we want to find that area or percent lower than scores of 8.39, we can use the fact that all percents are going to add up to 100% because this is a probability distribution, and we can calculate 100%, subtract 16% equals 84%. We can check these in StatCrunch. So if you prefer to use StatCrunch and not the 68, 95, 99.7% rule when you're doing your homework, that is just fine. So I'm going to come into StatCrunch. I'm going to open a blank StatCrunch. I'm just going to be using the normal calculator. I don't need to have a data set, so I can click that open StatCrunch and have a blank file like this. And then I go Stat Calculators, and there are calculators for all the different shape distributions that are common in statistics. Our class, we focus mostly on the normal distribution because that's the most commonly used distribution in statistics. And I'm going to go ahead and click on normal, and up comes a graph that'll help me find the areas. So I need to put in the mean and standard deviation for this problem. So our mean for the test scores of 7th graders, their vocabulary test scores, was 6.84, and the standard deviation is 1.55. Now, one of the questions I just solved asked what percent of scores were above 8.39. So I'm going to pick greater than here. You can click on your inequality and choose less than or equal to or greater than or equal to. Because there's so many scores and 8.39 is just one decimal, it does not technically matter calculation-wise whether we had a just greater than relationship here or greater than or equal to. You could think about the idea that 8.39 is just one score, so that one decimal score wouldn't have much of a measurement. It's like a piece of paper, but we're thinking about the accumulation of all the scores. So I type in that x value I'm investigating here, 8.39, and hit compute. Now in my worksheet, I had 16% higher than 8.39, but here in StatCrunch, I have 0.15865, so this would round to 0.16 or 16%. So what StatCrunch is doing for us is doing more exact calculations, and so you can see if we put in 0.16 here and hit compute, StatCrunch would fill in the exact x value. And so really, really close, it gives us an x value of 8.3814097. So that's because our 68, 95, 99.7% rule uses a little bit of rounding in it. I'm going to put this back at 8.39, and then my area over here goes back to 0.1586. The areas are always in decimal form. And then if I want to know the area less than 8.39, I just click on my inequality and switch direction. And there is my 0.8484%. You might notice here in the normal calculator, there's a spot for the 68, 95, 99.7 tick marks. So you can go ahead and click there, and they show up here on the distribution. They rounded a little bit differently. They went to 1 decimal place. I went to 2 decimal place, but overall, the values are close. The differences are usually just due to slight rounding differences. All right, if we want to know where that middle 68% is, we can go to between, and we are not thinking about these scores 1 and 1. Those are just default values. And then we cleared the area and put 0.68 and hit compute, and we get the lower value and the upper value. Now, we had said 5.29 to 8.39 using our estimates. StatCrunch gives us a little more precise values, but very, very close. In our class, it's okay to estimate or approximate using the 68, 95, 99.7% rule. If you want to check the 95%, we see it's a little bit different, and that's due to rounding and slight differences. So this 95% value corresponding to 2 standard deviations here in part C, that's a little bit rounded. It's not quite 2 standard deviations. So our scores that we estimated, 3.74 to 9.94, were very close, but a little bit different from StatCrunch.